This one's kind of interesting. Maybe a little bit harder of a middle riddle. So we have triangle ABC, and then we draw the tangent at A, and we see where it intersects BC. So is that line like harmonic with the symmedian? So let's see. Tangents. So like, I think there's some theorem that this line is harmonic with the ABAC and the symmedian. Is that true?
Yeah, that is obvious.
Yeah. Yeah, no, yeah, it's obvious. M is the midpoint of arc AC. Not containing B. So we draw the midpoints of these two arcs. The midpoint of arc TC. Do they mean the midpoint of arc BC? Let's see. So this is M. I think they might mean the midpoint of arc BC. I'm going to try that just for now. So N, M and N. AN intersects TC at D. And R is the midpoint of AB. We want to show that CR is perpendicular to MN. So MN, there's a lot of like theorems about MN, I think. So like we can use the in-center X.
And it's not that point you drew in.
Or M is not that point?
Yeah. N is the midpoint of arc TC of circumcircle TAC.
Oh, TAC. How do you know it's well, I guess maybe you're guessing that it's TAC, right?
If it does not contain A, then
it would be TAC. Yeah.
Yeah.
Okay. All right. I'm gonna redraw that. Yeah. Okay. So let's change point N. All right. So M looks okay. So we have TAC. Okay. So this will be N. I'm going to shrink it a little bit. Shrink triangle ABC. Maybe move it over here to make more room so that we can see N. There we go. So this is going to be N down there. And AN intersects TC at D. And R is the midpoint of AB. And we want to show that CR is perpendicular to MN. All right. Let's check that that's true. That looks good. And I see Ryan just joined again. So thanks for coming back on. All right. So we have AT. And then let's draw this. And we We can draw this. Okay, so this isn't a bad diagram. I don't think this is the symmedian, is it? Though I'm not sure. Guess we could check. So if I draw the tangents of B and C, looks like it could be. No, I don't think so. These look like they intersect. Yeah, it's not the symmedian. Okay. I was gonna say that would be a weird criterion. All right. So we want to show CR is perpendicular to MN. So yeah, I'm just going to clarify this if anyone's watching on YouTube. But yeah, I agree. It kind of has to be if it's worded that way. Okay. So there's a couple things we could do. We could try to show that Cn squared minus Cm squared is Rm squared minus Rn squared. That's one way we could do this. So yeah, so this is an angle bisector here.
One thing which is probably useful is that AM passes through midpoint of arc ABC.
Okay.
That is an angle trace.
Arc TAC.
ABC of circumcircle ABC. So it contains B. AN.
Sorry, you said AM passes through the midpoint of arc.
Well, it may be true also. I wanted to say for AN. But
this one?
Yeah. It may be true also for AM and TAC.
So AN passes through the midpoint of arc. Which arc?
AC, which contains B.
Oh, the midpoint of this arc. Okay. So FA is equal to FC. Okay. And then let's see if EC equals ET. That looks like it's also true. So yeah, we have a lot of isosceles triangles here. So FM is perpendicular to AC then, because FA equals FC and MA equals MC. And then this almost looks like an orthocenter kind of. So we know these are perpendicular. So maybe I could draw on that right angle. And oops, let me do it the other way. So we have that right angle. And then we know that EN and TC are perpendicular. And I'm guessing that's also an angle chase. That's not too hard. Does that give us any orthocenters or something? Maybe EHC and MGC are similar. Just a guess. I don't know if that's true. Yes. And is that obvious?
Yeah, an angle trace.
Okay. Yeah, now I see the angles.
We actually have similar quadrilaterals. So ETNC and MAFC. I believe.
Okay. So ETNC and MAFC are similar. And that gives us a lot of information. Maybe we could use like the gliding principle. Okay, so a spiral similarity about C takes one to the other, right? So we want to show CR. What if we only take that spiral similarity part of the way? But yeah, this angle wouldn't be equal. That's the thing with that.
RG is perpendicular. I mean, parallel to BC.
Ah, good point. So yeah, this is a right triangle, angle MAN. And I wonder if it's similar to these right triangles. Let's see. So yeah, this angle right here, AMN is 65.56. And this angle here, oops, I did it the wrong way. I don't think it's the same actually. 52. Basically, if we drop a perpendicular from R to BC, then we want to show that that triangle is similar to triangle AMN. So let me do that. Because R is the midpoint of AB, so if, yeah, it might help to drop perpendiculars. This point refuses to be drawn in GeoG. Okay, I think it'll work now. So we want to show angle CRI. I think we want to show angle CRI as angle AMN. Whoa, I did not mean to do that. This one. I think if we show CRI as AMN, that would work. Oh, it's not true. I think this is 60 something. Oh, I got confused. Okay. So yeah, I'm just gonna delete these because yeah, we know they're similar and we know those are right angles. So CGH, because GH is also parallel to AT, right? Yeah, GH is parallel to AT.
I think we can just consider about triangle ATC and just forget about point B. Like if we redefine the problem to be let ATC be a triangle inscribed in a circle and let N be its midpoint of the arc TC and let M be a point such that AM is perpendicular to AN and also MA equals MC.
Okay.
So what's left to prove is that MN is perpendicular to CR, which we don't even need point F, point like the point where we defined originally.
Yeah, we can hide a lot of stuff. So I guess we could keep that point if we want, but this is a right angle is what you're saying. We don't really need point B. You don't really need this. We could leave that if we want. But yeah, so triangle ADC, N is the midpoint, this arc, and then M lies on the perpendicular bisector, so that this is 90 degrees. So yeah, so yeah, so this is 90 degrees and M lies on the perpendicular bisector. And then we want to show CR is perpendicular to MN. Yeah, we could. Yeah. Yeah, point B is kind of irrelevant. Well, no, but we need point B, right? Because we need to know this is tangent, don't we? Well,
we can take M such that AMC is angle TAC.
AMC is angle TAC. Yeah. Okay, so we don't even need this circle basically, is what you're saying. We want to use that this is a right angle, that's the thing. Okay, so F, I got rid of F. Yeah. So CM squared minus CN squared, that would be AM squared minus TN squared. We're going to show AM squared minus TN squared is RM squared minus Rn squared. So I wonder if this is just a Pythagoras bash. Let me write this out. So we want to show if the midpoint of AT is on the circle AMN. Interesting. So yeah, it's this point I, right? So Ryan just messaged this to me. So midpoint of AT. Oh, this looks like APMO, Asian Pacific Math Olympiad or something, where we had to show these points are cyclic, MAI and N, and it's like a spiral similarity. So if we know that, maybe that solves it.
Yeah, they are equivalent.
Okay. Showing that this is cyclic is equivalent to showing those are perpendicular.
Yeah, it's just like an angle chase.
Okay. All right. So let me write this out. CN. So that would be TN squared minus AM squared. I want to show that's Rn squared minus Rn squared. So, okay, all right. So I'll try to do, so Ryan, do you know, so what was your proof that this was cyclic? I think this might be APMO, Asian Pacific Math Olympiad. Oh, is it just the, I'm trying to think. Take the reflection of N over I, and we have congruent triangles. Okay. Let me think about this. Which triangles would be congruent? So I'll reflect it, but I'm not sure yet. Okay, so N prime is the reflection of N over I. Let's see. MAN prime and MCN. All right. That looks interesting. Okay. Okay. All right. So I am going to write up some stuff here. Let G and I be the midpoints of AC and AP. So I, R, and G are collinear. And then let n prime be the reflection of n over I. Then an prime equals an, sorry, I don't think that's right. So am is equal to cm, so mn prime is equal to mn. Oh, but we don't know that yet. Okay, so we don't know yet that MA is equal to MN prime is equal to MN, but we know that AM equals CM. I think we actually haven't proven that yet, but it's not hard to prove. Yeah. So AM is equal to CM and AN is equal to, okay, and then it's just angle side angle. So MAN prime is equal to MCN prime. AN prime equals TN because okay, yeah, AN prime equals TN from the parallelogram, which is equal to CN. Since AN prime TN is a parallelogram. And okay, and then we do an angle chase to show MAN prime equals MCN. Because MCN is MCA plus ACN. ACN, and that should be equal to MAC plus okay, so this angle right here is basically angle NAT plus angle ATN, which is 180 minus and TNA. Okay. So MAN prime is equal to yeah, how do we get that? So this is a reflection. I'm trying to figure out how to get MAN prime. Maybe I'm missing something. Oh, we know this is 90, right? We know, okay, we know angle MAN is 90. I think that's where I kept getting confused. So it's 270 minus angle NAN prime. Which is 270 minus, that would be twice 90 minus INA. Okay. So that's 180 minus twice angle INA, or 180, sorry, 90 plus twice angle INA. You have to show these are equal. So MCA is oh, I think it should be TNA. Let's see. Yeah, TNA, which is TCA. Okay, so NAN prime. So I'll write it like this. It's 270 minus because NAN prime is 180 minus TNA. Sorry, this is taking me a while. So which is TNA is angle TCA minus 90. Or this would be equals angle TCA plus 90. We want to show that these are equal. MCA plus ACN. So and yeah, these are going to add up to 90 because angle EC, yeah, okay. So MCA is ECN. There we go. Oops. Plus angle ACN. Yeah, this took me a long time. ECN plus wait, MCN is MCA plus ACN. Yeah, I see why these are equal. I just gotta. So let me write it like this. This is angle TCA plus angle this is TCA plus MCA plus TCN. Which is TCA plus ECT. TCA, which is TCA plus 90. Okay. All right. So let me break this up into 2 lines. So it's going to make me do this. Let's see if this works. Oh, but then it makes it look all weird. I will get this. Don't worry. It's going to take a second. There we go. So these two are equal. So MCN is equal to MAN prime. So those triangles are congruent. And then once we know that, then we know that angle MIN is equal to 90 because MN equals MN prime implies angle MIN prime equals 90. So I'll write it out in one line like this. So MN equals MN prime. That means that angle MIN is 90, which means that you have a cyclic quad. So MAIN is cyclic. And then from there, we can show CR is perpendicular to MN. It's probably just an angle chase, right? Let's see who's on.
Yeah, it is angle chase. You need to show that NRC is AMN.
NRC is AMN.
In order to get the 90 degrees, which will get the cyclic quad.
Okay.
And
right.
AMN is TIN. And that is immediate that we have TIN is on NRC since ATN and ADC are similar.
Okay. So yeah, once I show that NRC is AMN, it's obvious. And then NRC, you were saying, sorry, how do I find NRC?
You take similar triangles ADC and ATN.
Okay, ABC, ATN. Okay, so I should draw B back in. Did you say ABC and ATN?
ADC, ATN.
Oh, ADC and ATN. Okay. Or I could do it this way. Angle CRD is NIT, which is MAN. Or AMN, of course. But CRD is NIT because since CAD, okay. Oh, I'd like that. Okay, I'll do it that way. So I'm going to copy what Khan put. But yeah, both ways work. I can't write that angle sign, but it's okay. Angle CRD is equal to angle, or copy paste doesn't work with the angle sign for some reason, but for the rest of it, it should. What? Okay, I have to type it out since and NAT are similar with corresponding medians. So then we have angle CRD is angle NIT is angle MAN. Okay, and from there, it's not hard to show that CR is perpendicular to MN. I'll elaborate a little bit more, but first, So I have this, this, this. Just making some room. So once you know that CRD is MAN, then it's kind of obvious, because I guess I could draw on this point, but it doesn't really matter that much. So that would mean MARJ is cyclic. And then it easily follows. There's a couple ways to see it at that point, but all right. So I'm going to move on to the next one. So thanks everyone for your help on this problem. And let's see what we've got. Okay, so here's a middle riddle, and we have a hard one here. So this one I feel like is not as hard as it looks, but I'm going to start with, this problem looked interesting, so I'm just going to start with this. See if I can maximize it. Sorry, I'm trying to maximize it. It's giving me a little trouble. Maybe there's a keyboard shortcut for maximizing. There we go. That time it worked. All right. So we have a triangle ABC. Yeah, if I can find a keyboard shortcut, I'll just use that instead from now on. So we have a parallelogram ABCD, and we draw the antipode of A. So first I'm just going to draw the antipode, then I'll draw the sorry. I'm not doing so great today. Sorry, guys. So we draw the antipode of A. So let's call it P, and I'll make this an O. So this is P. And then I see, where do BP and CP intersect the sides of the parallelogram? So maybe I'll make it like this. So I have this and this, and I'll draw on the rays, and I want to see where BP and CP intersect them. So that's BP, and that's CP, and it intersects them at X and Y. This is D, so I'm going to draw that first. This should be X. This should be Y. And the parallel from D to BC, we want to see where it intersects AX and AY. Okay. At T and S. And T, and this is S. And we want to show that SX, TY, and AB concur. So it looks like maybe Cheva's theorem. Yeah, I don't know why P's in blue if it's like a fixed point. It's kind of interesting. But I will make these lines look a little nicer. All right. So we have BPX, CPY, and then we have the sides of the parallelogram. And then we have this. So yeah, Cheva's theorem is maybe the most obvious way of thinking about it, but maybe there's some other way of thinking about it too. I don't know. So these are right angles. So P is the orthocenter. P is the orthocenter of BCD. And A, E, and B are collinear. So maybe we could draw the orthocenter of ABC or something. Yeah, so really, we really don't even, well, yeah, we should draw point A. But actually, yeah, because we need point A to find point S and T. I wonder if we could just use similar triangles a bunch of times, because if I draw this and this, we could try to find SD over FB, and then BP over GC, and then AY over YS, and then AX over XT by similar triangles. So yeah, SD over SY is FY over FB, and BT over XT is XG over GC. And then we would need to find AY over AX and show it's like equal to some ratio of those. Maybe that's not the best way of doing it. Oh, it's raining hard outside. I don't know if any of you guys can hear it.
Oh, this one, we just use harmonic bundles.
Okay.
Can you extend XY to meet ST at a point?
Yeah. Okay, and then we want to show these are in harmonic conjugation.
Yeah, that is true. And that is the same as saying that oh wait, let me let me think about it for a second.
Okay.
Can you let AD, can you connect AD?
AD.
Yeah, let AD meets XY at a point.
Okay.
So we need to prove that HD, SD are in harmonic conjugation, which is the same as proving the cross ratio HI YX equals -1.
Okay.
So if we take D as the center of the bundle, we need to prove that DB, DC, DE, DH is equals to -1. And that is true because E is the midpoint of BC, and
It's
H2 is
parallel.
parallel to
Oh, that's yeah. Okay, then the problem's really obvious. I just didn't see it. Yeah, good proof. So let xy intersect st at h, and let AD intersect BC and XY at E and I. E and I. Then HDST is equal to HIYX. Is this the first time we've used projected geometry here today? Might be.
I think Doldes-Argus involution theorem counts.
Oh, yeah, geometry. That would count. You're right. Projecting through D onto BC. HIYX is equal to, oh yeah, we'd have to do infinity. So BC, the point at infinity, I goes to E, and then Y and X go to B and C, and I'll just rewrite this as BC. So we can swap the two. Well, really, it would be this: C, D, E, dy, which is -1, and that's since E is the midpoint of BC. BC. What? Oh, because I have to do this. Wait. BC. Is it not like how? Oh, because this one has to be a curly also. All right. And then I need to fix this. There we go. So that means that SX, so T is -1, and that means that SX, TY, and AD concur. All right. Very nice. So we can either do this or we could go back to the problem we didn't solve. Which do you guys want to do?
Let's do the new one.
The new one. Okay. So this uses isogonal conjugate. So you start with any 2 points that are isogonal conjugates. So what if I do this? Well, nah, I don't want to do that. So P will be 1 point, and I'll draw the pedal circle. Then I will draw Q. So let's draw the pedal circle here. And then I'll have to draw some perpendiculars. Let's see, check the chat. Oh, finishing this one, or the one we did before.
Yeah, this one.
Okay.
The one that you are drawing. Yeah, this one.
Okay. So, sorry. perpendicular. There we go. Okay. So this is going to be point Q right here. E and F. Oh, nice. Oh, but I switched the letters. So close. E and F are the projections. And F is the X is this point. And AP intersects the circle again. Okay, so let me make this look a little nicer. Hide a bunch of stuff. It almost looks like AP and B aren't collinear. Okay. So E, F, whoops. And then X is this point. I could draw this point too. All right, so those are isogonal conjugates. Here is the circle, and AP intersects it at point G. So I'm going to want to rename this. Let's call this K right here. All right, so we have a half hour left. And this will be the center of the circle. Oops. Let's call it O. And okay, so AP intersects the circle at, that looks better. AP intersects it at point G. And then we draw the antipode of G. And G prime X intersects the circle at T. And we want to show that EF, GT, and BC concur. So yeah, it's kind of a very general configuration. Oh yeah, GX intersects it at T. All right, so maybe it's easiest to let EP intersect, or EF intersect BC at a point, and then we want to show, yeah, like maybe I could draw something like this. That looks pretty good. And we want to show that GT passes through that point. Call it I. Yeah, I like how general this configuration is. It almost looks like P lies on the altitude here, so I'm going to move P just a little bit. But yeah, when I do that, then the figure is not as nice. So, The rest of the figure looks the best when it looks like P's on altitude. Maybe that's okay. So yeah, we really don't even need point Q. We could just let X be the other point of intersection of this circle with yeah, they could just instead say draw the pedal circle of P and let it intersect it at B and X like this. And we don't really need K and H. Let's check the problem. All right, so we can use harmonics. We could try using the radical axis theorem. How else? Maybe sorry.
Take the foot of altitude from X to EF.
Okay.
It will rely on AT.
Okay. Is that a well-known fact?
It is not well known. I mean, I don't know how to prove it.
Oh. That's really interesting because that's just a very general fact about the pedal circle. Like it's just saying, yeah, if you have a pedal circle and you take like one of the other points of intersection, well, how do we define T? Yeah, okay, it's not that simple of a fact. But yeah, let's see. Maybe we could use the radical axis theorem here. So we have GT X. Maybe not. Yeah, we know this is cyclic right here. We know all three of these are cyclic. Does this point, does I lie on this? No. All right, let's see. Yeah, these problems, there's all these lemmas about isogonal conjugates that I just don't know.
Stefan, how exactly did you prove that J lies on AT? Is it an angle chase?
I haven't proved that J lies on 80.
Yeah, he just noticed it, but he hasn't found a proof yet. Maybe we could work backwards. Like we could let IG intersect the circle at P prime. And then we could try to show G prime X and T prime are collinear. I kind of like that because like I and G are defined pretty simply. And then maybe it's like a homothety about G or something. So O is the midpoint of G prime. And then if we take the midpoint of GT prime, so yeah, I guess it's the same as saying if we take the midpoint of GX, we want to show that, I guess that would be kind of obvious. So yeah, we know the center of the circle is the midpoint of PQ, although I kind of hid Q, so. I'm going to draw this in. I think it might be a well-known fact that these are. Oh, but yeah, it depends how we define things. I mean, basically, we want to show GTX is 90 degrees, right? That's what the problem is equivalent to. We want to show this is a right angle. So, I mean, that would allow us to hide, a couple things. So AP meets the circle at G, EF meets it at I, IG meets it at T. So yeah, are there any kind of cyclic quads? Oh, so that point J is, yeah, probably, this is probably how you noticed it, right? Because, I mean, IJXT is cyclic, right?
Oh, yeah. I mean, yeah, that's why I added it.
That's why you added it. Yeah. And then you happen to see that those happen to be collinear. So yeah, basically we dropped the I wonder if we could show these are collinear, if that implies this is cyclic.
I don't know about why, but I remember that there was a problem like similar to this we did on the session.
Yeah, I know there was some other one that we solved that had like
the point J, like the yeah, like where you let xj perpendicular to EF. Yeah, I think we met it somewhere before.
yeah, I know we did sometime on my channel. So let's say we know that these are collinear. We still have to prove it, but with that, let's see if we can show that implies it's cyclic.
I'm just afraid that if somehow the proof of AJT are collinear, just use the fact that EF, BC, and GT are concurrent, so everything will be messed up.
Yeah. But the way I kind of defined it here, I said let EF and BC meet at I, and let IG meet this at T. So yeah, I could call this T prime, I guess. Is there another point on the circle? Let's see. This point, or J is the most natural one. Like I could let this meet the circle, but I don't know what that would, how helpful that would be. It's right here. If I did this. Yeah. No, that doesn't do much. At this point, um, I'm just, I don't know.
Yeah, we met the point J before on the session. J, I only know one lemma about that point is that J lies on the radical axis of a circle with diameter BE and CF.
Oh, interesting.
Yeah, but I don't think it's somehow relevant to this problem.
Okay. Yeah, because this BE and CF.
And plus, if you unhide point Q, then AQ would be perpendicular to EF.
Okay. AQ is perpendicular to EF, or the circle, or
EF.
oh, interesting. Is that just an angle chase?
Yeah, just use the isogonal conjugate
Yeah.
and just
Because yeah, angle, yeah, it seems like yeah. So we could show xj is parallel to AQ. We could try to show that. And yeah, QX would be tangent to this circle in that case. So if A, J, and T were collinear, we don't know they are for this point. Like maybe we could let QX intersect AT. Yeah, I don't know. That's a good problem. It's a very general configuration. Seems like this is the way to go, though, showing that this is cyclic. If I had a guess. So if Q lies on the tangent, maybe we can use power of a point, because like what if we let this intersect this? We use power of a point. Yeah, I don't know. But yeah, I don't know if there's really anything special about this.
I have another observation without proof.
Okay.
Take the perpendicular from G to BC.
Okay. Why does it do this? Sorry. That was a perpendicular bisector.
And intersect it with EF.
Okay.
Then BMJC is cyclic.
BMJC. That is interesting.
That brings us one step closer to powerful point.
Okay, because IM times IJ. Well, yeah. IM times IJ is IB times IC. And then maybe we could use that on, which is IG times IT prime. So GT, it looks like GT prime MJ is cyclic, probably from that. Yes. Oh, does L lie on that circle? That's interesting. Oh, no, it doesn't lie on it. Okay. All right, we have 4 minutes left, and then I will finish the session. Yeah, I wonder if there's anything with like poles and polars here. So okay. I wonder what the polar of Q is with respect to that circle. Polar. Yeah, I don't think it's anything that special. Eight. See if this is still on. Yeah, I'll keep working on this after the session. It looks like a fun one.
I still think that AJ and T are collinear is the key to the problem somehow.
Somehow, if we know that, then that might help show that this is cyclic. Yeah, that does seem really useful. All right, so I think I'm going to stop here. So thanks for everyone who participated on the session. Thanks for all your help and for some very nice solutions. And for everyone watching on YouTube, thanks again. If you want to join us in the future, feel free to email me at mgreenb801@gmail.com. We meet every Sunday at 8 a.m. US Central Time. So thanks again and have a great day. I will stop the recording.
See you next time.
See you next time.